Good morning, everyone. I'm Rahul Chowdhury, and welcome to our comprehensive course on storage management. Today, we're going to dive deep into one of the most fundamental aspects of operating systems, how computers store and manage data efficiently. Let's begin with storage management fundamentals. Storage management is the backbone of every operating system, responsible for organizing, storing, and retrieving data across different types of storage devices. It's what allows your computer to seamlessly access files, run programs, and maintain data integrity. Now, let's examine the storage hierarchy. This is crucial to understanding how modern computers optimize performance. The storage hierarchy is organized in layers, each with distinct characteristics. At the top, we have CPU cache, the fastest storage available, but also the smallest. This is where the processor stores the most frequently accessed data and instructions for immediate use. Moving down, we have RAM, random access memory. It's fast and provides medium capacity, serving as the primary workspace where your operating system and currently running applications reside. Finally, we have secondary storage hard drives, SSDs, and other persistent storage devices. While slower than RAM, they offer the largest capacity and retain data even when power is off. This brings us to the key storage management concepts we'll explore throughout this course. Notice the fundamental trade-off. As we move down the hierarchy, we gain capacity but lose speed. Understanding these trade-offs between speed, capacity, and cost is essential for effective storage management and system optimization. Building on our storage fundamentals from page 1, let's now dive deeper into persistent storage. This is a critical concept that forms the backbone of modern computing systems. Persistent storage refers to data storage that retains information even after power is removed from the system. Unlike volatile memory, such as RAM, persistent storage ensures your data survives system reboots, power failures, and shutdowns. This is what allows us to save documents, install programs, and maintain our digital lives. Now let's examine the two primary types of persistent storage devices that you'll encounter in modern systems: hard disk drives and solid-state drives. Hard disk drives, or HDDs, use mechanical components with spinning disks and moving read-write heads. They offer high capacity at a lower cost per gigabyte, making them excellent for bulk storage. However, their mechanical nature means slower access times and higher power consumption. Solid-state drives, or SSDs, use flash memory with no moving parts. This gives them significantly faster access times, lower power consumption, and better durability. The trade-off is higher cost per gigabyte, but prices have been steadily decreasing. NVMe SSDs represent the latest evolution, using the PCIe interface instead of traditional SATA. This provides ultra-low latency and high bandwidth, making them ideal for high-performance applications and enterprise workloads. To properly evaluate storage technologies, we need to understand key performance metrics. Latency measures the response time per operation, how long it takes to complete a single read or write request. Throughput indicates how much data can be transferred per second, while IOPS, input/output operations per second, shows how many discrete operations the storage can handle. Understanding these metrics helps us choose the right storage solution for specific workloads and performance requirements. Now that we've explored persistent storage fundamentals, let's dive into file systems, the critical layer that sits on top of storage devices and makes data organization possible. A file system is essentially the method by which an operating system organizes and manages data on storage devices. Think of it as the filing cabinet system for your computer. It determines how files are stored, accessed, and organized. The core functions of any file system include data storage organization, deciding where and how to physically store files on the device, access control to determine who can read or modify files, and space management to efficiently utilize available storage capacity. Different operating systems use different file system types. NTFS is Microsoft's modern file system for Windows. XFIR is commonly used in Linux systems. APFS is Apple's newer file system for macOS and iOS, and FAT32 remains widely used for compatibility across different systems, especially on USB drives. Understanding file system structure is crucial. Inodes store file metadata and location information, directories organize files hierarchically, and metadata tracks file attributes like creation time, permissions, and size. These components work together to create the file system's organizational framework. Finally, file systems support fundamental operations. Create new files and directories, read existing data, write or modify content, and delete files when no longer needed. These operations form the foundation of all file management activities we'll explore in detail next. Now that we've covered the theoretical aspects of file I/O operations, let's dive into how these concepts apply in real-world storage management scenarios. Today, we're focusing on storage management in practice, where we'll explore actual implementations and strategies used in production environments. First, let's examine database storage optimization strategies through a detailed case study. We'll see how the I/O operations we just discussed directly impact database performance and learn specific techniques to optimize storage layouts for different workload patterns. Next, we'll explore virtualization and RAID configuration methods. You'll discover how these technologies build upon the fundamental storage concepts we covered earlier, providing both performance improvements and data protection through redundancy. We'll also dive into performance monitoring and troubleshooting techniques. This is where your understanding of the I/O stack becomes crucial, knowing how to identify bottlenecks and optimize system performance in real-world scenarios. Finally, we'll discuss capacity planning best practices. This involves predicting future storage needs and implementing scalable solutions that can grow with your organization's requirements while maintaining optimal performance.